Let's find the integral from 1 to infinity of dx over cube root of x minus 1. And I'll give you a few moments to think about it. Actually, let me change the limits for this question from 2 to infinity. From 2 to infinity of the given problem. Dx over cube root of x minus 1. Take a moment. So let u be x minus 1. Then du equals dx. So this is the same integral as integrating du over u to the 1/3. In other words, we need to integrate u to the negative 1/3 du. Right? Again, we learned so many complicated techniques, but this was just a simple u substitution question. So now let's just apply the power rule. So add 1 to the power, or add 3/3. So we have u to the 2/3 divided by 2/3 or times 3/2. And don't forget to bring the u back in terms of x before you look at the limits. And the limits are from 2 to infinity. So what happens is we deal with the first limit. And remember, anytime one of the limits is infinity, technically we're taking a limit as x goes to infinity, because infinity is not just a number. So what happens when you substitute the upper limit, when you take a limit as x goes to infinity of this quantity? What happens? Infinity minus 1 is still infinite, right? Infinity to any power still going to be infinity, times another positive number is still infinity. So what we're getting is infinity. Minus, now substitute a 2 in there for x. We're going to get 1 to the 2/3 times 3/2. Basically a finite number. Doesn't really matter that much what it is. A finite number, so infinity minus a constant, and the answer is infinity, right? I think I once saw a cartoon in a math journal. It said, Hotel Infinity, there's always room for one more. Because, infinity plus a constant, we're still getting infinity, etc. Okay, how about the next one? How do we solve that integral? Any suggestions? I could try to apply fancy techniques like trig substitution or maybe partial fractions, things like that, but there is no need, because this one actually works with u sub, right? Let u be, and let that be always your first choice. Try to apply u sub when it's a problem, or a simple formula if there is a formula. If none of these simple techniques apply, then think more complex. In this case, let u be r to the 4 plus 1, right? Then du equals 4r cubed dr. And r cubed dr will be du over 4. So first I will factor out that 8. And for r cubed dr, I'm putting du over 4, pulling the 1/4 outside. And the bottom is now u squared. Right? Simple u sub question. Right? So now we have 2 times the integral of 1 over u squared du. We don't even need to, apply the long power rule, meaning if you already know what is the integral of 1 over u squared. Negative 1 over u, right? So now we have negative 2 over u. Before plugging the limits, bring the original variable back, u being r to the 4 plus 1. And now let's worry about the limits. Okay, first the upper limit of 1. We're getting negative 2 over 2, in other words, negative 1, minus now the lower limit of negative infinity. Okay, as r goes towards negative infinity, what happens to this quotient, negative 2 over r to the 4 plus 1? Negative infinity raised to an even power, what will happen to it? Think of negative infinity as something like, let's say, negative 10 billion, something like that, just to see the patterns emerging. If you raise it to an even power, it's going to turn into a very large positive number, right? You're adding a constant, is still going towards infinity on the bottom. And so you're taking a ratio now, a constant on the top over something that goes to infinity on the bottom, so the ratio goes towards where? 0. So now we have 0 from the second part, so the answer turns out to be -1. Okay, another example. This one should help you with one of your group activity questions. Any questions about this solution before we try another one with improper integrals? Okay, so the question is integrating from -infinity to 2 of, it is from -infinity to -2 of 2 over x squared minus 1 dx. As always, let's not be intimidated with these infinite limits of integration. Let's just concentrate on the problem itself, the anti-differentiation problem. What technique could we use there? U sub is not going to work, right? There is no x dx on the top. What else could we try? I heard trig sub and I heard partial fractions. Chances are both of those methods could be used here. But I think partial fractions is going to be easier. Partial fractions will be easier. Exactly. We can begin by factoring it as x minus 1 times x plus 1. So this problem can be written as a constant a over x minus 1 plus another constant b over x plus 1. Again, we've done many of these kinds of questions in that section when we covered partial fractions. So we get common denominators, so multiply the first top and bottom by x plus 1, and the second top and bottom by x minus 1. And we're setting the numerators of both sides equal, because denominators will already be equal there. Okay, so and to solve for a and b, what method would you suggest I do here? Let's plug some values for x. In this case, I'm going to use 1 and -1. So did we all get our a's and b's for this question? I got a's 1, b's -1. If you flip them around, in the beginning maybe you have a over x plus 1, b over x minus 1. Your constants will be flipped as well, but it doesn't matter. You'll have two same fractions as I have on the board. Okay, integrating this is very easy, right? That's the whole purpose of partial fractions, so that we end up with something easy to integrate. But now we still have to worry about the limits, which were from -infinity to -2. It's not going to be a problem plugging the upper limit of -2, but when you deal with the bottom limit of -infinity, which will turn into positive infinity in these absolute value signs, you're going to end up with something of the form infinity minus infinity, and that is indeterminate form. Is there any way we could try to simplify it before we try to plug in our values? Yes, Joshua?
We should put the x minus 1 over x plus 1, because that's one of the properties of logarithm.
Okay, so let's use the property of log, and if you have ln a minus ln b, it's going to be ln a over b, exactly. So we're going to have ln of x minus 1 over x plus 1. At least now we got rid of the infinity minus infinity type of a situation, and it should work out a little bit easier now. Okay. You always wonder, why do we have an absolute value sign when we integrate a ln function? So it really comes into play when you have limits of integration, and especially a negative value. But I think even in this case, you have negative over negative, it still turns out to be positive anyway. But in case you end up with a negative value within an ln function, the absolute value ensures that it's going to be well defined there. So let's plug in negative x, rather negative 2 for x. Okay, what will happen? So I'm getting ln of 3 there. What will happen now if I substitute negative infinity for x on the top and the bottom here? Basically, I have something like of the form negative infinity over negative infinity. So which is another form of L'Hopital's rule, because the negatives, you can always take it outside, factor it outside. So you have like infinity over infinity in a sense. You can either use the rule you learned from Calc 1 to quickly find that limit, or use L'Hopital's rule. Do we remember if you have infinity over infinity, how do you find the limit of this inner part, x minus 1 over x plus 1? What is the limit of, first of all, just the inner part? 1, right? Degree of the top equals to the degree of the bottom. Take the ratio of leading coefficients. Suppose you forgot that rule from Calc 1. Now you have infinity over infinity. You know L'Hopital's rule, right? Differentiate the top part, what do you get? 1. Differentiate the bottom, you get 1. Once again, 1 over 1 is 1. But that is within an ln function. Don't forget that. So now you have ln of 1. Again, this time we dealt with something of the form negative infinity over negative infinity. Basically, L'Hopital's rule applies even when you have like infinity over negative infinity or things like that, because a constant, a negative value, you can always factor it outside of your limit. It really is not going to change the expression that much. So you can still use L'Hopital's rule when you have slight variations of infinity over infinity with another constant in there. So what is our final answer then? ln 1 is 0, right? So what is our answer? ln of 3. Yes. Okay, one more example on improper integrals. Once again, I'm going to give you a little bit of time to think about it. So if you're watching it online, please pause your video. If you're in class, just take a few moments. If my dv is e to the negative x dx, what would v be? Exactly, negative e to the negative x. Technically, you're dividing by -1 when you anti-differentiate, when you integrate, but that just shows up as a coefficient of -1. Okay, so the rule tells us the u times v minus integral of v du. Minus integral of v du. V brings another negative. Simplifying that quantity, plus the integral of e to the negative x dx, and integrating it once again. At this point, you know whether or not you've used the right technique, because if this becomes more difficult integral than you started with, chances are you picked the wrong u and dv. Go back and maybe switch them around. This should be easier than the original problem, and indeed it is, right? So we have negative x e to the minus x, and the integral of e to the negative x, once again, is negative e to the negative x. And now we're going to worry about the limits. But before I bring them in, I'm going to go ahead and factor out e to the negative x. And the limits are from 0 to infinity. When you're dealing with infinity and with negative exponents, I find it much easier if you can drop the negative exponent, the expressions with negative exponents into the denominator. That way, it's just easier to see the results. So that's what I'm going to do. I'm going to rewrite this as negative x minus 1 divided by what? e to the positive x, right? Going from 0 to infinity. Okay. Once again, when the limit is infinite, we're literally taking a limit as x goes towards infinity. In this case, we're going to have the top is going towards negative infinity, the bottom is going towards infinity. It's one of those versions of infinity over infinity, basically. How can we resolve that limit? Or do you actually see by looking at it what's going to happen there? Basically, the exponential function grows much faster than the regular x function. The bottom is going to infinity much faster than the top, and the ratio is going to go towards 0. But now let's explain it with the L'Hopital's rule. Okay, so if you have infinity over infinity, or negative infinity over infinity, you would differentiate the top and the bottom separately, right? Differentiate the top, and what do you get? Negative 1. Differentiate the bottom, you still have e to the x. Now, where does this go as x goes towards infinity? A constant over infinity, and that will go towards 0. So, minus, now let's plug in 0 for x. And e to the 0 is 1. So we're getting negative of negative 1 over 1, or positive 1 once again.